Good morning, everyone. I'm just getting things set up so that we can record our next video. And this is for section 8.4. So I think I'm almost set here. Here we go. So as you know, we've been working our way through Unit 7, Chapter 8, where we're looking at proportional reasoning. And in section 8.4, we took a look at scale factors, in particular, how they related to the area of figures. And that's, of course, with two-dimensional areas. So when we think about similar figures, we have a conversation bubble here and it's getting larger. We've got the area of one and the area of another. These are similar figures. How could we use the scale factor to help us understand what the areas actually are? So we're going to take a closer look at that in this lesson, where we solve area problems that involve similar two-dimensional shapes. The vocabulary that we're looking at is the same as it was for our previous lesson. We're still talking about scale diagrams, scales, and scale factors. So we're still using these words and making sure that we understand how to use them properly and what they mean mathematically. So be on the lookout for those as we go through the lesson. Now, what we're going to be taking a look at is a situation where we're creating a quilt. Being from this part of the world, I know all of you know what a quilt is. The quilt that we're going to be looking at is a lady named Norma is actually making it. She's making a quilt by sewing together congruent pieces of cloth, and in particular, square pieces of cloth. So it's going to be a simple, square, checked quilt. Now, in this situation, to make a larger quilt, she sews together more congruent shapes. So rather than sort of enlarging everything, she's going to start with a square. That's one sort of size, and then she's going to make it double the size and triple the size. And what we want to do is take a look at what the scale factor is as she enlarges her quilt, and then what the areas become. And we're going to record that in a table. And by the way, those of you who missed the class, there was a classwork page that you can use to fill in. So make sure you pick that up for me in class. Okay, so the question that we're really asking ourselves is, how does the area of the larger quilt relate to the area of the original quilt? So, as I said before, suppose Norma uses square pieces of fabric. And we're just going to use simple squares. It's not going to be fancy looking at all. Okay, so starting with one square, we're going to add enough squares to create a larger square that has double the original dimensions, and then we'll fill in our table. Okay, what does that mean? Okay, so here's my first square. And what I can see is this square has a length of 1, a width of 1, its area is 1. And this is a tiny little square. It might fit over my Barbie doll if I have a quilt for this guy. So he's the original one, a length of 1, a width of 1, and an area of 1. Now, we're going to do, as we said in the previous one, we're going to take this and add enough squares so that we actually double the size of our quilt. And so in order to do that, that means I'm going to need a square beside this one and one on top and one beside it. It would look something like this. So now if I look at it, I have a length of 2, a width of 2, and now my area is 4. And I have a new blanket. This one might fit over my stuffed teddy bear. It's a little bit larger. So I'm going to fill in my table that I have with that. And so here you have the first one, the length of 1, the width of 1. The scale factor hasn't changed at all, so we could say it's a 1, and the area is 1. The next one was a length of 2, a width of 2, scale factor of 2, and an area of 4. Okay, now starting with this same one square, add enough squares to create a larger square that has 3 times the original dimensions, and fill in your table. So if we did something like that, we're going to have to add squares, and so that we end up with 3. 3 squares along the bottom, 3 squares along the side, an area of 9. And by the way, my scale factor, I've now made it 3 times bigger. So if I fill in my table, a length of 3, a width of 3, a scale factor of 3, and an area of 9. All right, now the question we have is, predict the area of a square that has 4 times the original dimension. Well, think about it for a minute or two. Pause the video if you need to. But it would be a length of 4, a width of 4. It's a scale factor of 4. It's gone from the original one, which was 1 square, and it's 4 times bigger. And now the area is 16. Now, looking at these numbers, the question is, how does the area of each new quilt that we make, how does it relate to the scale factor and the area of the original square? So let's look at our table. So how does the new one relate, the area of the new one, relate to the original area and its scale factor? So if I think about the original area of my square being 1, and I did for the next one, there was a scale factor of 2, my area was 4. And then I looked at the next one. I had an area of 1, my scale factor was 3, my new area was 9. Had an area of 1, a scale factor of 4, and my new area was 16. I want you to pause the video and think about it. What is the relationship here? What's going on? So the conjecture that we make actually is that it seems like, if we look at this, it seems like the new area is equal to the scale factor squared times the original area. Interesting conjecture. And so that's a fairly easy example. So what we're going to do is take a more complicated situation and make sure, does this conjecture actually work? So we're going to use a shape like this one where we're trying to find the area of this donut shape, the blue shaded part. I know that I have a radius of 2 and a radius of 1.2. I want to find the radius of this shaded in part. And then I'm going to check to see what happens if I make these radii twice as big. So instead of 2, if I make this one 4, and instead of 1.2, I make this one 2.4. So let's see if our conjecture is actually going to work or not. So here's the work where we figured it out. Here was the conjecture that the new area equals the scale factor squared times the original area. So the area of my original donut, I'm going to call it, is the area of the large circle minus the area of the small circle. We know that area of a circle is pi r squared. So we're going to do pi r squared for the large radius minus pi r squared for the small radius. So I plot my numbers in, use my calculator, and get my number. Now, according to my conjecture, I'm going to try finding the new area using my conjecture. So I take my scale factor, which I'm going to use a scale factor of 2, and I'm going to square it, 2 squared, times the original area, and I get a number of 32.17. But now I'm going to make sure that that's actually the correct amount. So I'm going to find the area of the new donut. Area of the large circle minus the area of the small circle. So I find the pi r squared of the large one and the pi r squared of the small one. My new large radius would be twice as big as 2, so 4, minus the area of the new smaller one, and twice as big as 1.2 is 2.4. I use my calculator, and sure enough, I found that my area is 32.17. So my conjecture has worked even in a very much more complex situation. I've tested it out. It appears that I actually have found a formula that will work. So how does the area relate to the scale factor and the area of the original square? Here's your formula. The new area is equal to your scale factor squared times the area of your original shape. So now we're going to take a look at 2 questions before you actually try things from your homework. And the first one is about a kite. Jasmine's making a kite from a 2 to 25 scale diagram. The area of the scale diagram is 20 square centimeters. And so what will be the area of the new kite? In other words, how much fabric will she need for her kite? Now, this is a bit of a misleading question, especially for those who understand what it is to sew. Because if you're going to sew a kite, you also have to have a little bit of extra material for the surplus seams. We're not really going to that detail in this question. We're just going to do the area of the new kite, essentially. So the numbers we need to remember is that the scale is 2 to 25, and that the area of the diagram is 20. She's starting with this small diagram and going to enlarge it. So let's take a look at how it works. Now, one of the things that I'm recommending you always do is start out by saying, okay, what direction am I going? Well, in this one, I'm going from a small diagram to the real kite. And then stop to think about it. Is this an enlargement or reduction? And clearly, if I'm going from the small diagram to the real kite, it's an enlargement. And then I pause to consider and realize, okay, my scale factor will have to be larger than 1. So then I set out to create the scale factor. I have the numbers 2 to 25. And so I know the 25 will have to be on top and the 2 on the bottom to make sure that my scale factor is larger than 1. And then I use my formula. So the new area of the new kite is the scale factor squared times the original area. So my scale factor squared times the original area, I have an area of 3,125 centimeters squared for my kite. Now, that's probably the most natural way to do this question, but I also want you to realize that you can do the questions in whatever order you want. Instead of considering that you're going from the diagram to the real kite, what if we did it so that we were considering going from the kite to the diagram? What we need to realize in that one is that now we're looking at a reduction because the real kite to the diagram is becoming smaller. So the reduction means that we have a scale factor that is smaller than 1. So when we set up our scale factor and organize the fraction, we need to make sure that it is a fraction that's smaller than 1, 2 over 25. So we use our formula. Now, what we need to consider in this one, the scale factor I've plugged in. But what I need to do from the diagram is realize that, okay, my original area in this one is the one I do not know. And I actually know the finished product, the diagram. So for the new area, I plunk in 20 and put the x for the original. If I use these numbers and use my calculator for it, I am still getting the same result for the area of the kite. So what this was meant to demonstrate for you was that it does not matter essentially which way you go, but you do have to stop and pause and think about, okay, if I'm doing it from this to this, am I enlarging or reducing, and what is my scale factor, as well as considering what your new area and original area will be. All right, I can see my battery's running out, but I think I should be able to finish this video before it goes, so fingers crossed. The next question has to do with taking a look at an image on a laptop as it's projected onto a whiteboard. So Jim's laptop has a monitor with the dimensions 9 inches by 12 inches. The image on his laptop is projected onto the screen of a whiteboard. According to the documentation for the whiteboard, the screen area is, and it gives us this random number. Now, the image on the whiteboard is similar to the image on the laptop. So, first of all, determine the scale factor used to project the images. So let's take a look at what we have. We're going from the laptop to the whiteboard. So we know it's an enlargement. That means our scale factor is going to be greater than 1. So let's watch and see what happens and make sure we get a scale factor that's greater than 1. The new area equals the scale factor squared times the original area. So the new area is the whiteboard area, and we pull that number from our question. Our scale factor is what we do not know. And then the original area of the laptop is 9 by 12. And so when we use our numbers, remember you're going to be dividing by the 9 by 12 and taking a square root. You should get an answer of 5.125. Now the second answer actually comes from the following, where they ask you to determine the dimensions of the whiteboard. Well, if we know the dimensions of the whiteboard is 9 by 12, we can use our scale factor of 5.125, multiply it by each one of these, and we should be getting our actual dimensions for our whiteboard. Okay, now just some important things to remember. This formula that we've learned only applies to two-dimensional figures. We'll look at three-dimensional later, so make sure you watch that. And the hint is to make these questions easily, always make sure you take notice of the situation. Where are you going? From what to what? And write it down. And then decide, is it an enlargement or a reduction? Write that down. And then decide on your scale factor. Okay, you should be all set for the questions in your homework. Here is your homework, and make sure you do this. It's really important, and that you bring your questions to class. Good luck, everybody. Have a great weekend, actually. Cheers.